Welcome to the second lecture on the flow part of the flow in porous media, continuation of what we started in the previous lecture on Darcy's law, Darcy's experiment, and then permeability. We did the analysis that Darcy started by having a sand pack for water filter and had different potentials on different sides of this sample. Imagine this is A and this is B. And we found that the flow rate of the water in this sand pack was found to be U average, which was flow rate over the cross-section area, was minus K permeability over viscosity gradient of potential. That for this 1D system, gradient potential is ddz or ddx, depending on what do we call as this reference axis. Now, in this lecture, I'm going to continue on the topic and complete the storyline of the single phase flow in porous media. One thing that we need to note is that velocity is a vector, and gradient operator applied to a scalar is also a vector. Gradient of potential, or if you don't have gravitational effect, it would be just pressure, thermodynamic pressure, is defined in Cartesian coordinate as ddx of potential, ddy of the potential, and ddz of the potential, if you are in three-dimensional Cartesian system. Similarly, velocity also is a vector that will have three components, ux, uy, and uz. As such, the Darcy law can be extended to multi-dimensional systems. For that, it would read u, for example, in x direction, will be minus k over viscosity d phi dx if k is a scalar quantity. If k is a scalar quantity, we see that u in x direction will depend on the permeability that the rock will have in that direction. Especially k can actually be different in different directions, which means that k can still be one quantity, one scalar quantity in x direction. That would make it kx. You can have permeability in y direction for the flow to be different than in the x direction. So in that case, the gradient of the potential in y direction would drive the flow, but the resistance or how easy the flow can happen in y direction could be very different than the rock property to allow free flow happen in the x direction. In real systems, for example, the third dimension would be the same. For convenience, I just write it for 2 dimensions. In reality, the u is a vector and k is actually a tensor. So k will have xx value, xy value, yx value, and yy value. And when multiplied by the gradient operator of, for example, in 2D, d phi dx and d phi dy, potential, this is potential, not porosity, potential, obviously, capital phi, which is here as well. Then you would see that ux can actually have a footprint of y direction gradient of potential too. And this is a specific topic that we will cover in upscaling lecture that will come after this. Nevertheless, you need to realize that if, for example, k tensor is diagonal then you only will have kx, or xx to be precise, and kyy here. The other off diagonals will be 0. That will be possible that they may not be 0 as well in real life. It's just a matter of upscaling that I will cover in the next lecture. But if k is diagonal, then you get to know that your ux, therefore, I don't want to write it any longer because I already have written it off. So in that case, then ux and uy will have their own permeability in front of them in x and y direction. I can also write it xx to be now and yy to be consistent with the tensorial coefficients. Now, this will be completed in the follow-up lecture. Now, when we have this, there is one important factor that we need to also remember. That Darcy's law, this is Darcy's law, is valid under certain assumptions. One of the most important ones is that it is for flow in laminar condition. So what does it mean to have laminar flow? To understand the different flow regimes, we need to understand what are the acting forces in the particles, on the particles of our fluid flow. We have inertial forces and we have viscous forces. The ratio between inertial forces to viscous forces will be called Reynolds number, RE. It's an essential fluid dynamics non-dimensional, dimensionless parameter or quantity, Reynolds number. It gives us a feeling about what's the ratio between two different acting forces on the fluid flow, viscous one and inertial ones. Inertial ones are related to the acceleration, deceleration, mass of the system, momentum. Viscous forces are the shear, are the resistance. Those are with the viscosity are being characterized and the shear acting on the fluid flow. For flow in porous media, Reynolds number is defined as the grain size diameter d, which is a characteristic length scale, multiplied by density and velocity, rho u, divided by the viscosity of the fluid, obviously, and divided by 1 minus porosity. That's the definition. Reynolds was also a scientist, an Irish fluid mechanics, hydraulic expert, who actually developed the concept of the dimensionless of force actions on the fluid of inertial to viscous forces, as we know as Reynolds number. As you see, the momentum terms, density, velocity, is in the denominator, and the viscosity, the dragging force of viscous forces, is actually in the denominator. And for that, you need also a length scale for porous materials, flowing porous rocks or sandbags. We take the grain size diameter as a characteristic length scale. Now, what we measure is that depending on the value of Reynolds, you can have different flow regimes. If your Reynolds number is a lot less than 10, you are in laminar flow, which means that your viscous forces are quite significant. Your inertial forces are not significantly higher than viscous forces. So the system is pretty much viscous dominated. If your Reynolds number is more than around 2000, you are in turbulent flow regime, because then your inertial forces are extremely bigger than viscous forces. So you're actually having acceleration, deceleration, and momentum would be mattering a lot. Anything in between would be considered as transition. Transitional flow, which is transitional from laminar to turbulent. Now, when we say Darcy's law is valid for laminar flow, it means that viscous forces dominate the system, and that means that we have this part here. But what about the systems in which we have Reynolds number almost like 10 or 20, 30? If we are working in subsurface flow regimes like geothermal or water hydrogeology systems of groundwater flow, Reynolds is much less than 10. Can be even less than 1, can be 1. It's really like creeping flow. It's really, really small. But if Reynolds gets to be big, inertial forces have to be also considered. We don't reach turbulent flow in the subsurface naturally, usually. The thing is that as Reynolds get closer to 10 or 20 or so, inertial forces can be also considered. And that's the study that Forchheimer developed the concept of. And other scientists, especially Ergans and others, they started to actually advance on this. So what's the storyline behind this? We know from Darcy's law that if I write drop of the potential over length scale, so grad phi, grad potential, I can write it as, for example, drop of, if it's horizontal flow, for example, potential drop would be like pressure drop over length. That's the grad phi minus. So this is a replacement of minus grad potential gradient or pressure gradient in this case. That is equal to, if I see my Darcy's law here, it says velocity, Darcy velocity is here, but also viscosity over permeability is the multiplier. So Darcy's law says that the pressure drop across your sample, that can be any sample that you want to have. So imagine you have a horizontal sample. I draw it somewhere here. That's your sample. It has pressure. There is a delta P happening over cross section L. A pressure drop of delta P happens across length L. The linear relationship between the pressure drop over L and U is established through Darcy's law, which is valid when you have Reynolds number very, very small, which means viscous forces are all the mattering forces that you have. But if Reynolds gets a bit bigger, you have inertial forces to be considered, and that's the correction that then the Forchheimer correction to this comes and says, you know what? Potential drop or pressure drop is not just a linear function of velocity, which is based on viscosity and permeability, a kind of a viscous drop, but also you have some coefficient of the momentum, rho u square, also to consider. If I write it vectorial, it will be vector of u times norm of u. So, but just accept my slightly sloppiness for the sake of a convenient lecture. So it means that you have a linear part and you have a nonlinear part, rho u2, which is the momentum part. So what are these factors? We know from the sandpack experiment of before, the Karman-Kozeny formula and our bundle of tube theory, we know that this K here, this K is known to us to be dP square over 150 phi 3 over 1 minus phi 2. That's my K, right? So I can actually take 150 out of this equation. So instead of writing directly 150, I am going to take it out and I'm going to write it like A. There is a coefficient A here. Fantastic. But then I need to find my B coefficient, the beta one. So the beta is a factor like B times 1 minus porosity over, so this is, I'm talking about the A here, and here now B, is 1 minus porosity divided by porosity cubic grain diameter dp. Now let's plug them in and write the final delta P over L formula. A is in the denominator, so comes up. So I get A, but then it's multiplied by the viscosity, and then I have 1 minus porosity squared to come up, so it will be 1 minus porosity squared coming up, and then I have grain size diameter to the power 2, and then I have porosity cubic here. That becomes the 1 over K. I am inverting it. This is a multiplier of U. Now I have the second term, which needs to be just typed in directly, which is B. So here it was A, now it is B. And then I have 1 minus porosity. Great. Then I have divided by dP. And then I have porosity to the power 3 times rho U squared. So the first term is nothing else than just the Darcy law. And the second term is the correction when I have Reynolds number high enough that my inertial terms are also considerable. Now I would like to arrange them all into a neat way so that I can make analysis. So I get the delta P over L here. So I am going to continue getting the delta P over L. And then I'm going to take some parameters from the denominator to the numerator. You see directly that I have grain size diameter here that I can take to the top from the denominators here. Then I have porosity cubic, 1 minus porosity to take. Fantastic, because there is 1 minus porosity at least in all of them, so I can take them all to the denominator. And then I have 1 divided by rho U squared. Now, if I bring rho U squared in the denominator, this does not have rho, and its U is linear, so it's not really U2. So it will be having a division by the velocity in the system. So if I write now what happens to the Darcy part of the equation, it becomes A, right? The A will stand here, but it will be mu 1 minus porosity, because it is here, mu remains here, 1 minus porosity to the power 2, one of it is denominator, another remains here, and then we will have grain diameter times rho times U here left, because U was to the power 1, not to the power 2, and I'm taking U to the power 2 here. That becomes then plus, see, 1 minus porosity is already taken, phi 3 is taken, dP is taken, and rho U2 is all here, which means this is just simply B. Great. So I put this coefficient of B in a way to the left-hand side and wrote it this way. Look what you get here. This is Reynolds number, inverse. So that means that delta P, pressure drop over L, times dP phi 3, 1 minus phi, 1 over rho U squared, is A divided by Reynolds plus B. You know what, my friends? This factor here is called friction factor. The friction that happens as a consequence of viscous forces and inertial forces. The Darcy part and the non-Darcy, Forchheimer based or Ergon's way of looking at it this way. So that's the non-Darcy but inertial effects. Which means when I plot the F factor over different Reynolds number, I do see at the beginning that when Reynolds is small, 1 over Reynolds becomes big, so that first term dominates the flow. So I see a linear with a slope of minus A, because this is A divided Reynolds, is mainly dominates part. And then we have all the way to around 10, we have the start of the transition zone all the way so that it gets to be B dominated, which is around more than 2000. And this is when you have fully B dominated inertial forces domination, which means when you have really developed a turbulent flow. And that's when B is, so it's 1.75 is found by experiments that were performed by Ergon. And the reference to his paper is, I'm going to put it in the comments of this YouTube video. The inertial effects that was reported was that A was found 150 by Karmakuzeni and others also, and then the B factor here is 1.75, which is almost like 2, which is exactly the dependency of the pressure gradient here to the rho u2 will be about 2. Will be the factor here, but this is actually, the dependency of the delta P with respect to the pressure drop over L will be proportional to the rho u2, which is the u2 here. But here the proportionality of the pressure drop over L is to the linear aspect of u. But here rho u, it's u to the power 2, which is the inertial terms are more dominant. Reynolds has a u in the denominator, that's why actually the proportionality here is only to the u. This actually has been studied in the lab also. At some points have been also confirmed that the validity range for Darcy's law to say that pressure drop is a linear function of velocity, Darcy velocity, is only valid for Reynolds smaller than 10, which is actually this part. And as you see, for example, there is one other element that you can actually quite interestingly study. The pressure drop over the length, which is this term, if you have only Darcy aspect, only the Darcy aspect, will say that you are linearly proportional with the velocity. So when you change, you increase velocity, you get a linear function with the velocity, and that would mean that then you have the potential drop over length as a linear function. However, what Forchheimer correction of the Darcy law says is that when Reynolds is more than 10, you will start to deviate from it in this manner, which means that for the same velocity, if you want to have the same velocity, the real pressure drop will be much more than what Darcy would tell you. Darcy says pressure drop associated to that velocity is this much. But the reality is that because of inertial terms, because of rho u2, rho u to the power 2, you will drop more energy in the system. Your pressure will drop more. So you have higher delta P over L than what Darcy would expect. So if you do a lab experiment, you increase your U, you observe that at the beginning you are linearly increasing your U with the pressure drop in the system, constant length, for example, and then apparently after some time, you observe that you need to have much higher rate, much higher pressure drop in order to get the same velocity scaling as you had before, it means that you are entering a zone that you have higher potential drop or pressure drop because of non-Darcy effects, because of inertial effects. This is the additional pressure loss due to inertial effects. So that's very important, that the nonlinearity comes from that. And here it is also observed that when you see that the Reynolds number before 10, you have linear relationship, which is A over Reynolds, but then after that you transition to a curve that becomes 1.75 mainly dominated, because it's so big that A over Reynolds will be very, very small. So that's the non-Darcy correction to the Darcy law for you to get to the full spectrum of when it is valid, how it is valid, etc. Before we end this lecture, I'd like to also mention one thing. Remember that permeability that we had before was based on the sandpack Karman-Kozeny or bundle of tube theory, was found to be the formula that actually I have also written it here too. In rocks that we have here, our pore sizes are about micron of meter size. So you can have dP nearly about, let's say, 25 micrometer, 100 micrometers, or even few, like 5 micrometers. So these are typical values for geological systems. You can have very, very, very tiny ones when it is a shale layer. This is a rock which is a shale formation. Cap rock is actually this rock. So you see that when you calculate the permeability, you need to do the dP to the power 2, which means micrometer, which is 10 to the power minus 6 meter, will be power 2, which will be 10 minus 12 meter. So it's very convenient to decide to define a unit of 10 to the power minus 12 square meter as 1 Darcy. 1 Darcy is 10 minus 12 meter square because we are working with micrometer systems, and when micrometer is squared, it will be 10 minus 12. So that's the scaling thing for you that I wanted to clarify in the beginning. And then later, Darcy is only valid for laminar flow if you have inertial forces also significant for more than 10, Reynolds more than 10. You will correct it with this ergon formula or Forchheimer correction, whatever you call it, is for inertial terms that has a coefficient rho u2, and that coefficient is modeled right this way, and you go back and do the mathematics of bringing the coefficient here of B, which is the momentum part, here to the left, to consider a friction function, which would be A over Reynolds. It actually is now very much fluid mechanics analysis, because we have 1 over Reynolds as friction for flow over obstacles, etc. That makes sense for us in the laminar flow. And when you go to the inertial flow, where inertial forces are also important, that happens also in larger bigger values of Reynolds number, you get B, which is 1.75 in this case, and then you can see all these curves that are reported in experiments. In your lab, especially in your core flood lab, when you impose the delta P over L, as you increase delta P, the pressure across this sample, as you make it bigger and bigger and bigger, you will see that the flow rate becomes bigger, 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 but the prediction of Darcy for the pressure drop will be smaller than what you will measure in the lab when you go to high Reynolds numbers, because there is an additional pressure drop due to the inertial terms. So with that, we are now done with the Darcy law and with correction due to inertial terms. Next, we go to this sandpack that Darcy designed, and we will start to solve the flow problem. First govern it and then solve it to understand what's the potential distribution and what's the pressure distribution and what's the flow rate in my system. Thank you very much for following me in the third record, and I hope you continue watching the next episodes as they come live. Bye.